I will present my PhD work on pricing mechanisms for local electricity markets and their impact on the local distribution in the market and the privacy and transparency. And this presentation will be based on the main findings of this publication that I have published with my colleagues Sigrid Bergholt and my supervisor Ruth Kali. The motivation of this work, I will assume that most of you are familiar with the concept of local electricity markets. Just to summarize, we are talking about a market on like the end user level, where now prosumers, possibly flexibility providers, either households or also maybe industry can trade flexibility or source of energy, which would be true. And one of the big research questions in this field is how we should price the traded or the locally traded energy. And there's loads of proposed pricing mechanisms out there in the literature. But the challenge is to actually compare them against each other because they are tested on different case studies, different conditions, different assumptions. So it's very hard to make a direct comparison when we are reaching that phase of actually realizing these markets and finding out which pricing mechanisms we should use. So our idea is to use some of these most established pricing mechanisms and test them on identical case studies, identical conditions. And the criteria we have decided to compare them against is based on, we see that despite environmental and possibly community aspects are one of the main motivational factors of joining a local energy community or a local electricity market, but we also see that the actual price has a huge impact on their resulting trading behavior and also their willingness to participate. So it's crucial to have a pricing mechanism that is perceived as fair by all the market participants in order to sustain an actual acceptance of the market and a willingness to participate. We also see that these pricing mechanisms is also often based on very complex algorithms, and transparency on how these algorithms work is also essential for the market participants to trust the final outcome and the resulting price, and also for them to make informed decisions in order to sustain a healthy competitive environment within the market. However, we also see that the complexity level of these pricing mechanisms can sometimes counteract to assume transparency of this market. So even though a lot of information is out there on how this pricing mechanism work, the complexity level makes it harder for the market participants to trust them still. We can, for example, see this with the wholesale electricity markets where a lot of information is out there, but it's so complex that people still don't trust the resulting price. Lastly, we also assume that a local electricity market will be utilized through some kind of digital platform that has to comply with some kind of data protection regulations or laws, for example, the GDPR in the European context. But research has shown that even though a platform is compliant with these regulations, the algorithms behind them don't always comply in practice. So it's very important to consider this aspect already in the design phase of the algorithms. So that's why we ask ourselves these questions. How do the different pricing mechanisms influence the welfare distribution in the local electricity market, and how or which one of them are most beneficial for prosumers versus consumers? Because a lot of studies consider the benefits for the community as a whole, but we also want to look at the distribution between different market participant categories. And lastly, we have this qualitative evaluation of their privacy, transparency, and complexity performance. Okay, so I will not go through the details here, but in the literature, we divide these pricing mechanisms into 4 main categories. And then we have chosen one of each of these 3 first categories, one of the most established mechanisms. We have chosen to exclude the auction mechanisms because you often have to know the utility function of each of the market participants, which we don't. And then it's also harder to directly compare with these other mechanisms where the prices are set by the algorithms themselves. So I will briefly go through how the different mechanisms work without equations. So The supply-demand ratio is a rule-based pricing mechanism, meaning that the price is set just based on a simple set of rules. And this is the only one that is a pricing mechanism on its own. It doesn't clear the market, it just sets the price. So we have chosen to combine it with a central market clearing problem in this case, which is just a simple linear program clearing the market centrally as a community. So the market participants, they report their net consumption into the local market platform, which solves the central market problem to trying to minimize the total cost of the community based on restrictions on individual and market energy balance, and also technical restrictions within the market. Then the market clearing results are sent to the supply-demand ratio pricing, where the algorithm calculates the net surplus of the market for each time step and the net demand for each time step, and then just divide the surplus on the demand. Then you get a number between 1 and 0. And that ratio or number is used to set the price between these two pricing bounds. And for all the pricing mechanisms we have used in this case study, we assume the same upper and lower bound for the price. The upper bound is what the consumer would otherwise pay if they didn't participate in the local electricity market, meaning the retail buying price, because we assume they wouldn't want to buy anything more expensive than that. And that is the spot and grid tariff in this case. And the lower bound is what the prosumers would otherwise sell their surplus for if they didn't participate in the local market. And in this case, that is the feed-in tariff. So that means that if the supply-demand ratio is 0, the price will equal the upper bound. If it's 1, it will equal the lower bound. And where between, the price will be somewhere in between the bounds. The next one is consensus alternating direction of multipliers method, which we will call CDMM from now on. That is based on the same central linear program that we used here. But now we decompose the program into separate optimization problems for each of the market participants. So we start with the local market platform sending a price signal to all the market participants. And we choose this initial price to be exactly in between the two pricing bounds, as we consider that to be the most fair starting point. And then all of the market participants solve their own optimization problem based on this pricing signal, and then report what they want to trade within the local market back to the platform. And then the local market platform checks if it's consensus between the bids, meaning that he checks if the amount wanted to be sold is equal to the amount wanted to be bought. If it's not, he has to send a price signal back to all the market participants, which is the price from the previous iteration plus this kind of penalty, which is based on this parameter, step size parameter, meaning that if the prosumers want to sell too much to the local market, he will get a lower price signal back because he has to reduce his amount, and the consumers will get a higher price if they want to buy too much from the market. And then this iterative process continues until we reach this consensus. Lastly, we have what we call the equilibrium problem, which is a mixed complementarity program. Again, this is based on the same central linear program, but now we use the KKTs to solve this complementarity program instead. So that means that the prosumer has to report both consumption, production, and technical info to the local market trading platform, which solves the dual problem for all the participants, and the dual of the energy balance constraints determines the local trading price. And this is based on the Nash equilibrium, and the price and market trading results are then sent back to the market participants. The case study we have tested all these pricing mechanisms on are just a simple local energy community with 10 households. We only have PVs in this case, no batteries. And we tested with varying degrees of PV production in the neighborhood. So case 1, we have a relatively low amount of PV production, and then we have a high amount. So in the graph here, you can see the green is the total demand over the year in the local community. And the purple there is the PV production in the high PV case. So you can see we have a lot of PV in that case compared to the community load. So the results in terms of welfare distribution, here we have chosen one random day to show how the different mechanisms allocate the resources or the trades within the local energy market. So we can, for example, see that the supply-demand ratio mechanism allocate quite randomly in order to minimize the total cost of the community or maximize the social welfare. Here we have to say that this is not a result for the supply-demand ratio mechanism again, because that's not what clears the market. That's just central market clearing problem. So that's not a conclusion for that pricing mechanism. The CADMM has a big winner-takes-all behavior, where you can see that the one offering the highest volume into the market or the lowest price essentially gets the whole trade. So here you can see that house number 10 gets a huge, or gets to sell almost all of its surplus, while house number 3 has to then sell to the wholesale market instead. While the equilibrium model allocated trades almost evenly. So everyone gets a small share each, equal share, and then they have to sell the rest to the wholesale market. In terms of prices, here we have plotted the price against the volume traded for that price. And we can see that, as expected, the supply-demand ratio distributes the price quite linearly between the two bounds. So with a high volume, it equals a lower bound. With a low volume, it equals a higher bound. We can also see that the CADMM just is quite flat in the middle. And this has two reasons. As I said, we start with this price signal, which is in the middle between the higher or upper and lower bound. With this small community and only PVs, it requires relatively few iterations to solve the market. So the penalties or the iteration is quite few. So the price doesn't deviate that much from the starting point. Also, this penalty factor or step size parameter has to be empirically set in order for the mechanism to converge at all. And the algorithm is quite sensitive to what that parameter is. You can have the same input, but depending on that parameter, it will either never converge or converge. So you can see that the prices here are quite biased in terms of what we put as this parameter and also the starting price. For the equilibrium model, this is based on the alternative costs. Remember, it was the dual of the energy balance constraint. So that means that if the surplus is lower than the total demand in the market, local prices will equal the upper bound. Immediately when we saturate the market or the surplus is higher than the demand, the price will fall down to the lower bound. So it'll be either the upper bound or the lower bound. In terms of welfare distribution among the market participants, we can see, we can see that the CADMM is very beneficial for the prosumers, not so much for the consumers, and then the opposite for the supply-demand ratio. And that is because the supply-demand ratio pushes the prices down towards the feed-in tariff, meaning that prices will be lower. And the CADMM never reaches this lower bounds, will be relatively high at all time steps. That means that the prosumers is better off in this case. We can also see that the cost savings are differently allocated between the prosumers again. As we saw, the CADMM had this winner-takes-all behavior. So you have some prosumers that get a lot more benefits than other prosumers. And we can see that this is linked with the ones having the highest net surplus compared to their net demand, meaning they have a higher PV capacity compared to their annual demand. For the high PV case, we see the same tendencies with a random allocation with the supply demand and an equal allocation with the equilibrium. And now we can see even stronger this winner takes all behavior with the CADMM, with now house 2 taking over the market essentially. And the prices is behaving in the same manner as with the previous case study. We can now see that the CADMM prices is unaffected by the different amount of surplus in the market. It's still there in the middle. And we can see that here, if you plot all the cases over the year, the prices over the year, both cases with the CADMM is equal, it's unaffected. which further confirms this bias towards this parameter or penalty size and also the starting price. In terms of welfare distribution, we now see that house number 2, right, take it over the market. In this CA&M, he gets almost all the benefits. House number 10, that was the winner in the previous case, gets very little benefits compared to house number 2, even though he has the same PV size as before, or the same investments as before. And we still see the same tendencies that CA&M is more beneficial for prosumers, supply demand is more beneficial for consumers, while the equilibrium is more equally distributing the savings or benefits between the market categories. So for the more qualitative analysis of this pricing mechanisms, in terms of information sharing and privacy concerns, the supply-demand ratio only requires information about net metered load in order to clear the market or set the price. And this is the same as the users already report through their smart meters, meaning that the information sharing is not necessarily more than what they otherwise would do when not participating in this local market. This information, however, is not required by the CA&M, but they have to report what they want to trade within the market. And that information is also shared not only to the market platform, but also with other participants. Yeah, so this information is also shared with other market participants, not only the market platform. However, it's aggregated into this average level. So it's not like very detailed information, but still in these small markets, it may be possible to identify other users through this information. And also the equilibrium, you need a lot of information to make it converge and to clear the market, basically all details. Yeah, as I said, you have to share only with the central entity with the supply-demand ratio mechanism at equilibrium, but additionally, you share information with other market participants with the CA&M. In terms of details, it's quite low with the supply-demand ratio. Again, only smart meter meterings, but very high with equilibrium. In terms of complexity, the supply-demand ratio is very easy to explain. It's very simple rules. But the CA&M is very complex to explain users why the price is what it is at this particular time step without going into this. Oh, we set this step size parameter to be 0.5 today. That's why the price is what it is. It's quite hard to understand for the users. And same with transparency on the actual price. You can explain why it is like it is with all the market or pricing mechanisms, but you will compromise some privacy information with both the CA&M and the equilibrium model because you have to go into the details of what the data was used. In terms of computational time, the supply-demand ratio mechanism excels quite substantially. The CA&M is very slow, but it's not paralyzed in this case study, which it will be in a real-life implementation. And also the equilibrium is quite slow and struggles a bit with convergence. So to conclude, the supply-demand ratio mechanism excels in terms of privacy and transparency and complexity. But it's quite clear that it favors consumers over prosumers, thus limiting the viability of the investments, for example, for the prosumers. The opposite is true for the CA&M, where most of the benefits go to the prosumers, the cost on the prosumers. It also has a high competition between the prosumers, thus limiting the benefits for some of the prosumers. And it's also heavily dependent on input parameters and this penalty factor, and also very complex and low in transparency. While the equilibrium is more even in the distribution of welfare, it's more economically efficient, but it has some major privacy issues and convergence issues that needs to be solved. in order for realizing it. And further work, we need to include storage, for example, how that will affect behavior, and also different pricing mechanisms and other evaluation